Hello. Till now we discussed the EMI sources in PCBs. We discussed the common mode and differential coupling, coupling through common impedance, coupling through the air, which could be in near or far field. So several issues regarding the EMC. Now, then we discussed what are the main sources on the PCBs in electronic circuits, and we wanted to minimize these noises by decreasing the loop areas and also decreasing the areas of the signals which has high voltage changes. So all that was in order to minimize the noise sources, but we cannot go beyond the limits. We have a physical dimension of the PCB, so there are certain finite loop sizes and also finite areas which are unavoidable. So the next step we have to do is to filter the noise which is left and minimize it even further. And today we will talk about filtering of noise with emphasis on conductive noise. So all the electromagnetic interference that is conducted through the common impedances through the cables, and we want to keep that noise on the noisy side of the circuit, not to spread to the rest of the circuit. And that filtering is one of the essential things to do to minimize the EMI. So every circuit that has some potential noise sources would probably require a sort of filtering as well. And with this filtering you can do really well or not. Depends what type of source you have of noise source, and consequently what kind of filter you're using, because not every filter is designed for every noise source. So you have to be really careful what is the noise source, especially whether it's voltage or current, whether it has high impedance or low impedance, and also what kind of EMI coupling mechanism you have, whether it is a common mode noise source, is a differential noise source. So all that has to be kept in mind in order to make efficient filter. And on the other side, you have to also consider the impedance of the victim. And all that then would give you the most proper filter to use. And this will be the topic of today's lecture. So EMI, electromagnetic interference filtering. Let's start with a few basics to get to know the terms. First of all, I want to show you what is insertion loss. An insertion loss is a parameter of every filter. If you buy it online or anywhere actually, if you buy a filter and use it in your system, first thing you will check is its insertion loss, and therefore we have to define it. So let's imagine we have a system like that. So we have a source, and this source would actually mean like it would be a aggressor. Let me see if it is working. Okay, yeah. So here we have aggressor. An aggressor has some sort of a source. Aggressor, 2 S's. That's a source, noise source, aggressor voltage. And this noise source has a certain impedance. So it has an aggressor impedance. We can actually make it as we can represent it as a Thevenin circuit. So we have aggressor source here, and we have a victim on the other side. Now, a victim has a certain impedance as well. So we can now define so-called factor, which would tell you what is the noise suppression? It is a suppression factor. So let's imagine we have a voltage here, which is the source voltage, and we have a victim voltage here. So let's name it a victim voltage. And this is the aggressor voltage. So what would be the victim voltage? It's quite easy to calculate. We can calculate the aggressor current, which is the same as the victim current, as a aggressor voltage divided by sum of two impedances. All right, so now we can define so-called suppression factor, which would be also called attenuation factor if you want. It's the ratio by how much the aggressor voltage is attenuated. So it's actually the opposite as amplification. So the attenuation factor is defined, and I will now type right here. The attenuation factor S is defined as the ratio between the aggressor voltage divided by the victim voltage. So the aggressor voltage now, if it is large and the victim voltage very low, then the suppression is very large. So large suppression means low victim voltage. It's the opposite as the gain, 1 over gain. The gain would be the victim voltage divided by aggressor voltage, and the gain would be then less than 1, and of course the suppression factor would be more than 1. How much is it? Well, if the aggressor current is aggressor voltage divided by these two impedances, then consequently the victim voltage would then be aggressor current times the victim impedance. Therefore, if we put it in this equation, we get that. We got that the suppression factor is this term here. It could be also equal to 1 plus Z aggressor over Z victim. So if the victim impedance is very large, then we don't have any suppression at all. If the victim impedance is very low, we have high suppression. Now, this is very similar to the capacitive noise coupling, when the large victim impedances would also mean larger noise coupling through common capacitance. Now, we can represent now another factor or another part which would define or which would represent a filter. Now we want to lower this noise and we want to increase the suppression factor. Therefore, we introduce a filter. A filter is a 4-terminal device which contains inputs and outputs, one input, one output, and it has some passive circuitry inside, which includes inductors, capacitors, maybe resistors, maybe some other unknown components which could be also beneficial to filtering. Now all that is designed to lower the output noise and on the same time not influence the wanted signal, because we have to know that usually on cables we don't use cables for noise conducting. We use cables to carry the required signals. So we don't want to filter these required signals too much. We want just to filter noise. Therefore, the filter has to be constructed in the way that it does not influence the signal we want to carry, but we want to filter the noise. Okay, I think I was clear enough here. So, when we introduce the filter, we also introduce the filtering as filter, the filtering attenuation. And the insertion loss is defined as the ratio between the filtering attenuation and the attenuation without the filter. So that ratio is later expressed in decibels. Therefore, we have 20 log. And that's the equation you have to remember. Now, the attenuation factor itself is then divided by the attenuation factor of the filter is divided by the attenuation factor without the filter, and the ratio between those two is insertion loss. That means the effect of loss of the noise due to inserting of the filter. Insertion loss. Okay, I think that was also hopefully clear enough. Now let's go further and have a few examples. Let's use an inductor as a filtering element. In order to calculate its insertion loss, we have to first calculate the attenuation without the filter, which actually we already know. Then we can insert the coil. Now that coil here is actually a 4-terminal device, which is probably like that. So it has an input and it has an output, even though it's just one single coil. Now that filtering element has a certain impedance, which we can actually calculate. And here it's quite easy. The impedance of the coil is J omega L. Now this J omega L impedance is now inserted in series, which means that the total impedance of my circuit would be a sum of 3 impedances: aggressor impedance, the coil, and the victim impedance. So calculating the current means summing all 3 together, and calculating the final attenuation, which would then include the victim voltage and the aggressor voltage, it's quite trivial here. The filtering attenuation is now the sum of 3 impedances over the initial impedance of the victim. And the insertion loss, if we now calculate the insertion loss, we divide those two and we get this equation here. This can be derived anytime, so I suppose you can do that easily. Now, what is the victim impedance and how to use it? Let's state that the victim impedance is constant and the aggressor impedance is constant as well. Okay. Now, let me draw you an expected insertion loss. I will here draw a graph. I hope this is fine. This here is the frequency, here is the insertion loss. So the impedance of the coil increases with frequency, right? At low frequencies, it is almost 0. So if this equation term here, J omega L, goes to 0, then the insertion loss is 1. And logarithm of 1 is 0. So 0 decibels, if we are talking about insertion loss in decibels. Okay, hate it. Decibels. Then we start with 0. What then? At high frequencies, the L goes to, omega L goes large, and therefore it increases the whole term, and the insertion loss increases as well. But there is some so-called corner frequency. What is that? The corner frequency is when the omega L equals ZA plus ZB. Then the term here is 1, so it's 1 plus J1, which would give you the square root of 2. A square root of 2 in logarithmic scale is 3 decibels. So the 3 decibels is the corner frequency, omega 0. All right. So that's how the insertion loss would look like if you put a coil inside. Well, that's in theory, because the coil, the inductance, in the real world is not ideal. Because if that inductance was ideal, then we wouldn't have any problems at all. Our insertion loss would go large with the frequency, and the filter would be great. So let's start with a simple simulation using ideal coil. For the source impedance, the aggressor impedance and the victim impedance, we took 50 ohms. And this is not arbitrarily chosen, because 50 ohm impedances are standard impedances used in filter testing. So these are source and victim impedances, and the coil inductance is 100 microhenries. And if we want to calculate what is the corner frequency in this case, the corner frequency would be 50 plus 50 ohms over the 10 to the minus 6 henries would be 10 to 6 hertz, so 10 megahertz, which would give a corner frequency of 159 kilohertz, because we have to divide by 2 pi. Okay, so let's check it out. That's the simulation, which actually represents the same thing as I shown in this sketch here. So the corner frequency when you get 3 decibels is less than 200 kilohertz, which would be correct. And then the loss factor, the insertion loss, increases linearly in the log scale, of course, and that's the ideal case. Now put some real elements into this story here, and the real elements would require at least 2 or even 3 additional components. The realistic coil includes series resistance, which is the resistance of wires, and parallel capacitance, which is a capacitance between windings. At least these 2, but probably also losses in the core. If the coil is not air coil, it is winded on a core, a ferrite core maybe, then it includes some losses there in the core. These are 2 losses, the hysteresis losses and the eddy current losses. So this is the parallel resistance of the coil, the parallel capacitance, and the inductance of the coil itself. So all that gives another story. First of all, I want to plot the impedance of such a coil. The impedance of such a coil, Z of the whole coil. At low frequencies, we have the series resistance. So the series resistance is at low frequencies because the omega L is much lower. So we have the series resistance. Then the impedance increases because the coil starts to prevail. So this is the omega L part. And then this capacitance, which is 1 over iot omega C here, would start to prevail at certain frequency. So we'll have some sort of a parallel resonance, omega P, the parallel resonance between L and C. So after that we will have 1 over omega C parallel, and that would go down again. Now there could be some series inductance as well, which is inductance of wires, which has almost non-parallel capacitance. So we'll have some sort of a secondary effect after that, which is actually shown here. Now, this is the main part, the main frequency, omega parallel, which will tell you at which frequency the coil becomes a capacitor. And this omega P is equal to 1 over square root of LCP, because this is the frequency when omega L equals 1 over omega CP. So you can easily derive it. I will actually drive it here. So here the omega P is when the omega L is equal 1 over omega CP. and that would then give you the omega p out of it. So this is an actual coil. The parallel resistance here defines the height of this peak here. All right, so let us do the simulation how the insertion loss would look like if we include a real coil. So we are including a real coil with some real values of winding capacitance, series resistance of wires, and the parallel resistance, which represents the losses in the core. And this is a result. So we have a parallel impedance here. We have the corner frequency, which is the same. So here the corner frequency omega 0, and again I will write all the equations here. The omega 0 is defined by the equation of the insertion loss. So I will also write an equation of insertion loss, which is 20 log, and here we have 1 plus omega L iota omega L over ZA plus ZB, right? So the omega 0 is where the omega L is equal to ZA plus ZB. So it is ZA plus ZB, ZW over the L. Okay, that's the omega 0. And the parallel omega is equal to 1 over square root of L C parallel, that one here. Now here we have a part which is actually defined by omega L, and here we have the part which is defined by 1 over omega C parallel. So omega L is here, here is 1 over C parallel. So our insertion loss at high frequency is defined by the quality of the, not the quality, but the capacitance between the windings of this coil. So the best coils are those who have the lowest capacitance. How you make them, it's another story, but it is a very important factor, because at high frequencies, coils which do not have a very well defined or even minimize the capacitance between the windings, they will not be effective at all. And of course, one other thing, if you even have a really good coil which you would use in your system for filtering, you might use it in the wrong way. You might route it in the way which would increase the capacitance between the primary and secondary pin, between the two parts of this coil. So you can use it in the wrong way and therefore make it less effective. Okay, what about a capacitor? We can also use a capacitor as a filtering element by, again, putting it in correct way. So first of all, let's start with the same thing, with the attenuation factor without anything. Again, it is a divider between these two impedances. Now we will add a capacitor. So what happens? The capacitor impedance is one over iota omega C, right? So we can again calculate the current through this, the aggressor current through this circuit, and the aggressor current would now be the aggressor voltage divided by the sum of these two impedances. The first one is the ZA, and the other one is the parallel connection between the capacitor and the ZW. A parallel connection means that you actually have to sum up the admittances. So it's 1 over the sum of the admittances. The sum of the admittances is J omega C plus 1 over ZB. That would be the current. And then finally you can use that to calculate the voltage on the load, which would be the UW. And voltage on the victim is this current times the, again, parallel capacitance and impedance of the victim. So you can do that, you can calculate that just for fun, and you will get the attenuation factor. The attenuation factor is a sum of the impedances on top, so the parallel connection between the victim impedance and the capacitance divided by the these two here again. And if we now go a little bit and simplify this equation, we get this. Now the filtering attenuation gets higher at high frequencies, as you see here. The omega is here. Okay, now we can calculate the insertion loss again by dividing the S filtering over the S0, and we get this. So here we have a parallel connection of load and aggressor impedance. So this is the aggressor parallel the victim and J omega C. So if we draw that, what we get? So if we use this capacitor as a filtering element and draw the, again, the insertion loss versus frequency, what we do get is at low frequencies, again, the omega goes to 0, so the insertion loss is 0. Then at a certain frequency it starts to increase and increases again. So the story is the same, but the capacitor is connected in parallel. And again, we can define the corner frequency, omega 0, which would be when the omega C ZA times ZB, ZW over the ZA plus ZW is 1. Okay, when is this 1? When this omega 0 is 1 over C times ZA plus ZW over ZA times ZW. Okay, now this can be calculated for any case. Okay, so let me do an example again. So the capacitor in this way acts very similarly as coil. Actually, it's completely the same in terms of insertion loss. So the question is that true? First of all, we have to ask, what is a real capacitor? So let's start with this filtering example again. Now we have the same 50 ohm source and the victim impedance. We have the 100 microfarads capacitance. That's the mistake here. I'm sorry, copy paste error. So it's a capacitance, of course. And then we will see what happens. So again, we can calculate the corner frequency. And the corner frequency in our case would be 1 over 110 to 6. The parallel connection between 50 and 50 ohms is 25, and this is 1 over 25 ohms. So the corner frequency, omega 0, would be 110 to 6 is 10 to 4. 1 over 25 is 0.04 times 10 to 4. It is actually 4 times 400. Would that be 400? 4 times 10 to 2, 400 hertz divided by 6 would be something in the range of 6.28 if we calculate the frequency F0. Okay, we'll do that. Frequency F0 would then be would be 400 over 2 pi, and this would be around 4/6, ne? 2/3, 2/3 times 100. So it's around 66 Hertz. Okay, we'll see what happens. Going back there, capacitor as the filtering element. Yes, it seems okay. So the corner frequency is here, around 66 Hertz. And then the insertion loss increases really quickly. So again, this capacitor is very good, even better than coil in terms of the this case here. So there must be a difference between the coil and capacitor. But first of all, let's check how the real capacitor would look like. A real capacitor has some other components as well. So we have a capacitance, then we have to add a series inductance, and we can add series resistance. And then we can have also a parallel capacitance. Very similar story than in case of coil. And again, this series capacitance can have some sort of a parallel capacitance as well. So many different capacitances and inductance as a non-ideality elements. So that capacitor, if we draw its impedance again, versus frequency, the impedance of capacitor, at very low frequencies, the impedance is very large. Actually, is defined by the parallel resistance. It is here. Because at very low frequency, the omega L is almost zero, the 1 over omega C is very large. So at low, then the impedance of the capacitance drops at with high frequencies, and this is the 1 over omega C part. Now we come to the point when the omega L starts to prevail. So we have omega L part, and here we have the series resonance. A series resonance is defined as 1 over square root of L series C. Now the omega L increases, and the value here at the series resonance is defined by the series resistance. Now omega L increases, and then we have the secondary effect where we have this CP starting to work, and the CP would then cause some high frequency oscillations. Not only one, because we have several parameters, non-ideality parameters that are influencing each other. So our capacitor is good as a capacitor till the omega S, then it starts to become a coil. How that looks in reality, I can show you in this simulation here. Now I'm adding this series resistance and parallel resistance and series inductance. And this is the result. So what do we have here? We have here a omega 0, which is the omega 0 is when there's starting the insertion loss equation. The insertion loss equation is 20 dB 20 log, and then we have 1 plus, I think it was J omega C, and then we have the ZA parallel with ZW, right? So when this omega is equal, omega 0 is when this part is equal 1, which means it is 1 over C ZA parallel ZW. Okay. And this is omega 0, which in our case is 66 Hertz. Somewhere here. 30, maybe it's 33. Who knows? 66 is more or less here. I will recheck that. Now here there's somewhere is the parallel series resonance, omega S. The series resonance is defined by the capacitor and the series inductance. So here we have the 1 over omega C part again, and here we have the 1 over omega LS part again. And here is the parallel resonance of this mutual inductance, capacitance between the windings of the series inductance here. So it is defined by the 1 over square root of LSCP and so on. So the capacitor is capacitor until here. Okay, the value here is defined by the RS, and that's more or less it. So our capacitor is now limiting the attenuation factor at high frequencies. What else? Well, we've shown that inductor and capacitor are both good for filtering, but they are limited by their non-ideality parameters. Now, what about the choice, which one to use? Because both are actually good. But the thing is, first of all, they are different regarding their idealities and prices and sizes, but they are also very different in terms of the impedances, which might be a little bit awkward, but let me show you an example of that. Even though they in this system represent a similar role, it is because the system was the same. You know, the usage of coil and capacitor, it's very dependent on the impedances of the system. And that's what I want to show you here. Okay, we have a filter, this filter here. And that filter is represented by the filtering function and input and output impedance as well, which we did not talk about yet. So let me try to repeat or to go through the term or through the what is the maximum energy transfer theorem. The maximum energy transfer theorem would say that the impedances of the source and the load, where the highest energy transfer is, should be equal. So equal impedances mean maximal energy transfer. Actually, the impedances should be conjugated equal, if I'm totally honest. Now, what does that mean? The thing is that if you want to make a really good filtering, that really requires a little bit of introduction. A good filtering, our area filtering, could be done by two totally different phenomena. You can either reflect all the signal back to the source, or you can dissipate the signal. So filtering means two things: reflection or attenuation. Now, when these two phenomena happen, if you use in your filter only inductors and capacitance, and if they are ideal, then you cannot have any energy dissipation, because the energy cannot be dissipated in ideal components. You have an energy of capacitor which is Cu square halved, right? So the capacitance energy is Cu square halved, and the energy of the inductor is Li squared half. So this energy can only be dissipated if you are including resistances here, because then the power is defined as U squared over R or I squared R. Now, all that is possible only if you have the resistances included in any form. They could be actual resistors, or they could be losses in core or in dielectric. Now, the best filtering is by either reflecting the noise back to the source, if that's a filter. Imagine this is a filter. So we can reflect or we can dissipate, and the best is to do both. So let me now go back to this story here. Now, if we have the filtering, okay, like that, and we have ideal inductors and capacitors, whatever they are, in any form you want. It could be like that, it could be like that, it could be anything or any other, but they are ideal. That this filter cannot dissipate energy, so it can only reflect it. So you cannot allow the current or the voltage here to enter. So what you can do, actually what you should not allow, you should not allow the energy to enter, or power. That means that you have to reflect current or voltage. So let me show you now the idea here. So the power has to be reflected here. And on the other side, you have the output current here, and you have the output voltage, which is UW. Now, also here you don't want to power be reflected here back, so that it does not come to the load. And you can do that by choosing the input impedances and output in the impedances in the way that they would be as different as possible. Therefore, the high insertion loss of this ideal filter, which cannot dissipate energy, can be only done by reflecting all the power back to the source. And this is possible if you can do the largest possible impedance mismatch, because matching the impedances would allow you the power to go ideally through. By mismatching them, you will reflect it back. So if you have a large source impedance, then your current would be low. That's okay. And if you want to get all the power back, then you have to use very low input impedance here, so that the voltage would be zero. So if I draw now a truth table here, I will try to emphasize that. So if the aggressor impedance is very large, so I will do something like that, ZA, ZB, then I will put Z input and Z output, like that. And now I will make a truth table. So if both impedances are low, and then we have one low, one high, one high, one low, and then we have high, high. And let me make these red so that they are distinguished. Then on the other side, if we have a low input impedance, a low output impedance, then the current will be large. And in order to make the current small, we have to use high input impedance of the filter. So then we will reflect the current back, or we will not allow the current to flow. And then on the other side, if we have a very low the victim impedance, so I will name that victim, sorry for that. If we have very low victim impedance, we have to have very high output impedance of this filter back again to minimize the current. So high here. And therefore continuing high, low, low, high, and of course at the other side low, low. So let me show you another example. If we have a high source impedance, then we have to have low input impedance in order to make the current small, voltage small. And on the output, if we have high output impedance, we have to use, high victim impedance, we have to use low output impedance again to make the voltage low. So all that would require knowing the source and the current output impedance. So the impedance mismatching is a key factor here. And knowing that impedance is essential. So how do we know what kind of impedance we have in a certain circuit? That's another story. We will come to that. So let me now show all the possible filtering options. All these possible filtering options are shown here, including capacitor and inductor. Okay, so these are the impedances we can calculate or we can deduct from it. The coil, if we just use the coil, it has high input impedance and it also has high output impedance. We are discussing high frequency impedances here. So the coil has omega L, so at high frequencies it would be high. On the other hand, the capacitor has 1 over omega C, therefore the input impedance would be low and the output as well low. So we have to think of it as a 4-terminal device. Like that. Here we can do the same. Low, high, high, low, 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 high, high. So what kind of filter we use? It depends where we use it. What are the impedances on the one side where the source of the aggressor is and on the other side where the victim is, according to this nice truth table here. All right. So let me show an example of filtering element where we have on one side the power supply and the impedance and a digital circuit. Now, how do we determine the impedances? Well, if we have a power supply, so maybe just to make it a little bit more clear, here we have a source and the power supply is usually a very good voltage source. So therefore its impedance is very low. Now, going on to the other side, we power a digital circuit, a microcontroller maybe, or something similar. Now here, this digital circuit, they say that it has high impedance. So why is that? Because it is actually composed of very, very large number of small capacitors. So here inside this circuit, we have a lot of small capacitors which are then switched on and off with a certain switches. So this is how digital circuit can be represented. Always charging and discharging a million of very small capacitors, and it behaves like a very noisy current source. A very noisy current source means that it has large impedance. Now, what kind of circuit we can use then? If we have a low impedance, here we would start with coil, which has high impedance. And here, since we have high impedance, we will finish with a capacitor. And we will put it as close as possible to this microcontroller to make it the current loop here as small as possible. Because not only that we want to achieve a filtering effect, we want to make the current loop, which is then causing radiation of this high frequency current, we want to make it as small as possible. On the other side, we want to keep the noisy currents away from this long line. So we can put this coil here, maybe we can put it here. Well, it depends. If we put it there, then this long line here would make an antenna, because let's say there is a part of noise here still present, because the capacitor is not ideal. So where should we put this coil? Here or there? And the answer is here, because we want to make this area for voltage noise coupling to the surrounding by a mutual capacitance as small as possible. So we will make this kind of filter here. And but that's only if this source, voltage source with low impedance, has some noise also present, we might use another coil here. But nevertheless, this is the filter we should use. A filter with inductor on that side and capacitor on the other. Choosing the filtering components might be really tricky. Why? Because the non-ideality of capacitors and inductors is not very easily defined, because they are more or less hard to measure, and not just hard to measure, also quite dependent on the way that you're using them in the circuit. So these parasitic values are hard to determine. The other thing is, it is quite hard to determine what are the impedances of your circuit to calculate precisely what would be the insertion loss. Therefore, you have to use some simulations. And there are some tools you can use, like SPICE, for example. But nevertheless, if you use SPICE for simulating the insertion loss, you still have to know how to model all the parasitics and how to model your impedances of your circuit. Therefore, for example, you can use also kind of component, I would say, online calculators, like for example Red Expert from Word Electronics. A Red Expert actually has a large database of their components, which include measured impedances of their coils, measure inductances, capacitances, with all the parasitics up to gigahertz. And you can choose your system here. I will now show you the picture. That's the Word Electronics Red Expert. And you can define the system of your filtering here with the source and the load impedance. And you can define what is the impedance you are actually having. You can type it in, and then you type in your noise attenuation you want at a certain frequency, and it will give you some ideas, some suggestions, what kind of element to use. And then you can see the impedance or the insertion loss, and you can then choose the right component. Here are two components, as you see, very different in terms of the impedance and also in terms of the series resonance. And some of them work to higher frequencies. Here the blue one, the red one works better at lower frequencies. All that is then up to you what to choose and what kind of element to take, what price, size, and so on. So this would give you a better idea how in reality these components would behave. But you have to still keep in mind that here the source and the victim impedances are given with very simple numbers, such as ohmic resistances, which can be, of course, really rough estimation of what actually happens.